This is the first week of firmware training, and I guess week 2 of overall training. So, um, uh, buckle in. We have definitely some stuff to go over and to show you. So last week, we introduced we introduced microcontrollers, so what they're about, what they're used for, and stuff like that. We also went over C++, and started to just go over the basics of it and how to use it. And we also covered a bit of prototyping. So this week, we'll expand a bit more on the C++ content. We'll go over interrupts, and we will also go over state machines. And then after that, we will have our lab. So let's continue with some C++. So our first topic for today are functions. So imagine you were writing a program and you had like 10 blocks that and that did a particular thing, and you found that those 10 blocks did a thing that you wanted to happen, over and over again at points in your code. Now, you could just, copy paste those 10 blocks into your main method every time you needed to use them, but that would make everything messy, and it'd be kind of hard to debug as well. Like if you spot if there was a bug or if something wasn't working, it'd be really hard to go back and see where everything went wrong. So a function is primarily a way of organizing code, and what it does, it allows you to put essentially a chunk of code and sort of just package that into what we call into a function. And so every time you need to run that block of code, instead of copy pasting that code into the main method, you can instead just use one line and call the function, and that will run the code. So how do you define a function? So a function has a couple parts. So from the left here, you have your function return type. Your return type can be any data type. It can be an int, which is a 32-bit integer here. It can be a double, a float. If you don't have anything to be there, or if you don't want anything to be returned from the function, you can just say void. Then comes your function name, and then parentheses, and then in these parentheses are your arguments go into those parentheses. So essentially, they're just the inputs into the function. If you don't have any direct inputs into the function, you can either type in void into those parentheses, or you can leave them blank. If you did have an input, say you wanted to input like an int x, then in the parentheses you would say int space x. And then it's to say you wanted to input one more thing like int y, then you would say comma int space y, and then everything just would be inside those parentheses. And then you have your body. So right after your function header, you open the body with a bracket, and then you just define here where statements is. You define essentially the block of code that you want to run, and then when you've defined, and then after that block of code, you can essentially return a value, and the value you return the type has to match what you said in the header up here, so in the return type. And what that does is it essentially passes a value back into the main method, or from whichever method you called the function from, or whichever function you called this particular function from. So say I said in my main function I said int x equals, and then say I had a function called power. Power takes in two arguments. It takes in one int, which is like a base, so that'd be int x, and then another int which would be a power, so int y. And what it would return would be x to the yth power. And so if I said int x, I could say int x is equal to power, and then in parentheses, say like 2, 5, and then close the parentheses, and then have a semicolon. And then this is when you're calling the function, not when you're defining the function. And you'll see a bit more of this in the lab. And what that would result would be x in your main function would have a value of 32, because that it'd be 2 to the 5th power. All right. Next, we have the variable scope, and this is really important when you're defining functions. So essentially, all this comes down to is, if you define a variable, where can you access it? Where can you treat it? And where can you change it? So the general rule of thumb is, if you define a variable within a function, then you can't access that variable from outside the function. So say I had a variable named like Tom or something. I'm not sure why Tom. So say I in my main function I said, okay, string Tom is equal to Harry Potter. So if I try to access what the variable of Tom from outside the main method, I couldn't do that. I would need some other way. Maybe I would have to pass that value through a function, but I can't access it directly. And so that's what's called a local variable. A global variable is different. You can define a global variable before you define any of your functions in your C++ file, and then you can access that variable. You can treat it, and you can change it from anywhere in the file, so within any function in that file. Your third type of variable is what's called a volatile variable, and it's essentially a variable that's used in your interrupt functions, which we'll get to in a bit. And this is different from local and global variables, and we'll sort of go over why. But compilers, they can check for variables that aren't local or global variables, and then it essentially designates them frequently as volatile. All right. And then I guess I can wait a couple seconds here just in case any questions trickle in. All right. All right. So our next topic is loops. So loops are a way of essentially repeating a block of code for some number of times. And we have a couple of types of loops. So our first type of loop is called a for loop, and it's typically used to repeat code for a fixed number of times. So say you wanted to repeat a block like 10 times, your best bet would probably be a for loop. So let's go over the syntax. A for loop has three main parts. So when you open it, you say for, and then say int I equals 0. So what this is essentially you're initializing a variable that will serve as your counter. And so this is essentially saying, okay, at the beginning of the loop, set this variable to 0. Then you have your condition. And what this condition means is this loop will keep running as long as this condition is true. So as long as I is less than or equal to 5, at the beginning of each loop, this loop will keep on running. And then here on the right is an increment. Now it doesn't always have to be going up. It can go down too. But what this third part is how your counter changes after every loop. Uh, a lot of the time, you'll see it just going up by 1. So the plus plus means it means essentially just take the variable and add 1 to it. And so at the end of every loop, I will go up by 1. And so this loop here, it will run for 6 times. For I equals 0, 1, 2, 3, 4, 5. And then when I becomes 6, this condition will become false, and then the loop will exit. And so sum will be 0 plus 1 plus 2 plus 3 plus 4 plus 5, which would be 15. Now we have a second type of loops called while loops. And while loops are essentially just the condition. And they're typically used not to repeat code for a fixed number of times, but to repeat it until a condition is met or not met. So the syntax of a while loop is pretty simple. It's just while, and then in your parentheses is a condition. And so in this case, just like the for loop before, it's as long as I is less than or equal to 5. So at the beginning of each loop, this condition is checked, and as long as that condition is true, the loop will run once again. And then when this becomes false, this loop will break, and the program will go on to the next thing. Now, if you want to sort of do the same thing with a while loop as with a for loop, you sort of have to add in those parts yourself. So in the previous for loop, we could say int I equals 0, I is less than or equal to 5, and I plus plus within the for loop, within the definition of the for loop itself. Here we have to set those ourselves. So here we say in the beginning of the while loop, before it actually starts, we initialize I to 0, and then for every loop at the end we have to increment I by 1, and this will essentially do the same thing in this case as the for loop before. All right, I can wait a couple more seconds just for any questions. All right. So now we have arrays. Arrays are a way to organize data. And what that means is that it's essentially a way to have just like a row of data. And that's how it's organized in the actual computer memory, and that's essentially how we can treat it. So say we wanted like a list of 10 integers, we could define an array of length 10, and that would give us our list. And then we would have to go in and change every value of every int in that array to be the value that that we want. So with an array, it has a fixed size at when you declare and when you initialize that array. You can't add like extra values to it. You can't take away that values from it. So so with arrays, you have to stick with what you had and with what you made it. And you can access an element of that array with an index. And so say we had so actually before I talk about how, I'll talk about why. So the first element of an array is actually index 0, not index 1. And then the second is index 1, third index 2, and so on. And why this is the case is because the way that an array is defined in memory, the variable, when you make an array and assign that to a variable, that variable is almost pointing to the first element of that array. And then the index is sort of your offset. It's saying, okay, from that first element, how far do we have to go to reach which element we want? And so the reason that the first element is at index 0 is because we don't need any offset to get the first thing in an array. And so that's why the indexing starts at 0 and not at 1. And then say you had an array length of 9, the index of your last element would be 8, not 9. And then how you access or change the value of an element inside an array. So say you defined an array called I don't know, ints. So say you defined ints to be an array of size 10. So if you wanted to get the fifth item in that array, you would type in ints and then open bracket, and then since you're getting the fifth element, that'd be the fourth index. So open bracket 4 and then close bracket, and then that would get you the fourth or the fifth element in that array. And then this goes over that syntax. So you can define an array with or like this. You have to define what data type you want that array to hold, and then the name of the array there. It doesn't always have to be named array, and it's probably not a good idea to always name it array, but just for the sake of this, it's named array. But this can be named whatever you want. And then in the brackets here, you have the size. And then say you wanted to define your array as having the values 0, 1, 2, 3, and so on until 9. And so what you would do, you could do that in a for loop, because you know that the array is size 10, and so you want to run a loop 10 times, and that's where your for loop comes in. And so how you access an array, as we talked about, you say the name, open bracket, and then have your index number here. Now this is a variable instead of a fixed number, but this is just as correct. And so what this is doing is so let's start off with the first time this loop runs. So the first time this loop runs, I is equal to 0. And so it's saying, okay, let us set the element of array at index I, which is 0, that's equal to 0. All right, and then the next time I would be 1 because of this increment, and then we would say this time let's set the element of array with index 1 equal to 1, and so the second element of that array would be equal to 1, and then so on until we step through the entire array. A really good rule of thumb is that you should always set a value in an array before you actually read that value, because essentially when you define an array, what might happen is that the memory that's sort of already there that the array takes up isn't cleared, and so you might have some values that that are just bad, and also you really just don't want like an array of like all random values or of all zeros, because it's not really that useful. So just make sure you always set the value of an array before you read from that array. All right. And so an array doesn't have to be just like a one-dimensional like list. You can also have 2D arrays or 3D or 4D or 5D. And what a 2D array actually is it's an array of arrays. So it might seem like a matrix, but it's better to think of it as an array of arrays. And so essentially you have and each row is its own separate array. So when you define a two-dimensional array, just like you define a one-dimensional array here, you can have that, and then you can have a second number in a second set of brackets to define that second size. So if you wanted a 2D array of 10 by 10, it'd be array open 10 close and then open 10 close, and then you would have a 10 by 10 array. And then when you want to access an element from that array, you define the row number first and then the column number. So say you had an array called X. So this top element would be accessed by X 0 0. This one here would be 1 0 2 0 and so on. And you can think of this as the first number is essentially telling the program which array to get the number from, and then the second would be what index of that array to get data from. All right, that was kind of a lot. I'll just wait a couple more seconds to see if there are any questions. Well, I'm already 38 minutes in. All right. So next we have structs, and a struct is essentially you can think of it as a package. It's like a box, and it frequently has multiple types of data that's used to define a package. So say we had a 3D vector. A vector is defined by three things. It's defined by an x, a y, and a z. And so what we can do is we can make a struct called vector3d, and its elements will be 3 values. So you would have a float of x, float of y, and float of z, and these would be your coordinates. This syntax here, you can always come back to it, but make sure that you follow this type of syntax when you make a struct. So type def and type def struct, and then those are just keywords. Open brace, define your data here, close brace, and then you have the name of your struct here, and then close it off with this semicolon. So how do you use a struct? So now that we've defined what a vector 3D is, we can make a struct that has the type of vector 3D. So here, what we have is essentially a variable called vector, and that vector is essentially a struct of vector 3D, and so that has your 3 x, y, and z variables. And then now here you can then say, okay, I want to change the x value of that variable. You can say vector.x to vector.x equals something, and then vector.y if you want to change the y coordinate in it, and you can do that with a z as well. And then if you just want to access them, say you wanted to like output the x value of vector to a variable called like x core, you could say x core equals vector.x, and then the x value in vector would be set there. Just like arrays, you should always set values in structs before you read them. All right. So that's a continuation of C++. That was definitely a lot of material. Again, if you guys have any questions, feel free to just post them in the chat, and I'll wait for a couple more seconds. All right. So let's get started on interrupts, and an interrupt, essentially, exactly what do you think it is, kind of. So what an interrupt is essentially a mechanism or a function, or it's sort of like a trigger almost, and it's essentially it's something built into processors to run a specific function whenever a certain event occurs. Now, what that mechanism is, it can be hardware, so it can be when you trigger like a pin, like when you like press a button, and that changes the value of a pin, or it can be in software, like if you have like a 10-second timer, whenever that timer ends, that can send a signal to the processor, and then that can be an interrupt. And so what the interrupt does is it essentially triggers a function, and that function is called an ISR, an interrupt service routine. And what happens is when a microprocessor or when any processor receives an interrupt, it will just stop what it's doing. It will run the function, the ISR, and then it will come back and pick up where it left off in the code that it was running. And so that's why it's called an interrupt. So the main advantage of an interrupt is that we can essentially have something that happens on a certain trigger, but we don't have to spend time and code and write code ourselves to see if that trigger has been activated, or if that device is ready. And so what an interrupt allows us to do is we can just keep on running code, and then when the device tells us it is ready, we stop, just run the ISR, and then come back. So how does an Arduino use interrupts. So there's actually a specific function called attach interrupt, defined as part of the Arduino code. And so what you can do with that is essentially say, okay, so you essentially assign it a pin to watch, and then you give it a function and an ISR to run when that interrupt is activated, and then you define your trigger mode. And so the trigger mode can be a couple of things. It can be either rising edge, falling edge, or change edge. And what this means is, so a pin is frequently a digital pin, and so when you read a pin, you frequently see if it's 1 or if it's 0. So what a rising edge means is that the trigger would be when that pin goes from 0 to 1. And a falling would be 1 to 0, and then a change edge would be either one. So if it goes either from 0 to 1 or 1 to 0. And so when that trigger happens, the main code will stop, the interrupt service routine will run, and then you'll just come back right where you left off. So you essentially have to have, so in your actual code, you define the function that you want to be your interrupt service routine before your setup and your loop, and then in the setup of the Arduino, you can essentially have this function here to attach the interrupt to a certain pin with a certain function, and then specify a trigger mode. And this documentation is also on the Arduino website. So if you don't remember this, that's perfectly fine. All right. So that was kind of a short section. Now we're going to get into state machines. I just realized that I was in dark mode the whole time. So state machines. And I'm not sure how many of you guys know about this crossing. Is essentially just like it's essentially just an intersection at Georgia Tech, and the voice is very interesting. And yeah, you guys have to hear it just to feel its magnificence. But state machines. So what is a state machine? In essence, a state machine is sort of a device that stores a status or a state at any given time. So say like you're like hungry or sleepy or like awake. So a state machine would say, okay, at this time I'm awake, or this time I'm sleepy or hungry. And what a state machine does is it essentially takes in inputs and then gives out outputs to interact with other devices. And what this allows you to do is essentially a very basic form of a memory, because a state machine, the output of a state machine is frequently based off of both the input and the current state, and the state changes based on which state you're at right now and the inputs. And so and if we look at this basic traffic light state machine here, say we start at red. As long as the timer is less than 20 seconds, we stay in the red state. When the timer hits 20, we go to the green state, and then a 15-second sort of time period here, and then we could go to the yellow state, 5 seconds, and then red state. And so with regular combinational logic, it'd be really hard to like figure out which color that traffic light should be. But with a state machine, since you know both the inputs and which state you're currently at, you can then determine, okay, where which state and which output do I go to from here. And so you switch states based on, again, your current states and on your inputs. Right. So what is a state machine for? Again, it's just a really basic form of a memory. And it allows you to use a sequence or a history of inputs to assign an output, not just your current input values, as you would see on like a regular like circuit. And then you can also, with the state machine, essentially restrict the behavior to certain actions based on your inputs. So say you want to like restrict the outputs of some state machine. If you based and you had like a fair number of inputs. So if you wanted to restrict the number of outputs, that'd be really hard, because you would essentially have to go in and say, okay, for each combination of inputs, I want the output to be this, and this, or this and this. With the state machine, that can be a lot easier if you define the output based on the state, and so you can essentially cut down how many actual states you have, which then cuts down the number of possible outputs, and so that can essentially just provide some essentially restrictions to the actual outputs of a system, even if you have like a ton of inputs. And so this is used like this can be used in a ton of places. It can be used like in a combinational lock. So say you got you got the first number and the second number and the third number, and so it can say, okay, I've got the first number, and so the second number I'm looking for is this. I've got the second number, third is this. And so then you can have that memory of which numbers have I gotten and which numbers am I looking for. And then that can also be used in traffic lights and crosswalks, as was shown in the previous slide, or the 2 slides ago. And then, of course, because we're in Robo Jackets, of course, it's used in robots. So a couple of the usages of state machines. It can make sure that things happen in the right order. So sort of just going back to the combinational lock example, you could say, okay, first I received this number, that's good. Then I received this number, and then this, and then our third and final number. And so it's sort of like that. You want to receive things in a certain way. You want to make sure that things happen in the right order, and so and typically this happens in startup. And so state machines can be really useful when you're trying to make that happen in startup. And then, of course, it can also be used to control robots better, again, by assigning the output based on your states, not just directly by your inputs. So like say, because our robot may have like a ton of inputs, especially if you're using like analog sensors. And so if you had to just use like a combinational logic, or like code for like every possible combination, that would not be fun for either you, the coder, or for the person testing the robot. And so if you instead define the output based on states, you can really make life easier by having that stability and that inbuilt restriction. And a CPU actually and a microcontroller is actually one somewhat complicated, actually a very complicated state machine. So your computer right now is a state machine. All right. So there are a couple of types of state machines. One is the Moore state machine, where the outputs are solely based on your current state. And there are also mealy state machines, where the outputs are based on both your current state and on the input values at that time. And so here in RoboJackets, we typically use a Moore state machine because it's a bit less complex and is just a bit easier to build and to use. So the inputs of a state machine can be pretty much any sort of input you can think of. Frequently, we use sensors or buttons that can give us like a digital value, so like a 1 or a 0. And that's where sort of the Boolean state transitions come in, because there's like a clear difference between a 0 or a 1, whereas if you had like a continuous sensor, like an analog sensor, the like when do you transition, but when do you stay in the state, that might become a bit tricky. But typically, our inputs are sensors or buttons, and then our outputs can be running motors or lighting up some LEDs, and really just all the outputs, all the typical outputs of a robot. So this is an example diagram of a state machine that robot wrestling uses. It's a bit more complicated than what it seems, but it's a pretty good starting point. So when we first start or reset the robot, we go into what's called an idle state, and the output, in this case, the output is the motors. And so essentially at this state won't make any output, and you can't do anything with it unless you press the start button. And so when you press the start button, that makes a transition to your search state. And so at the search state, your motors are like currently stopped because you don't know where to go. If you detect something on the right here, so I have like a sort of like a small legend here. So det left means detect left. So if you detect something on the right, you go to the turn right state, and in the turn right state, the output of the motors is set to right. And then you're in this state until you stop detecting something on the right, and then you go back to the search state, or someone presses the stop button, in which they go back to the idle state. And then if it detects something on the left, same thing, except left, it just it goes to the turn left state, as long as and then when it stops detecting something, it goes back to search, and if the stop button is clicked for like an emergency or something, it can automatically just go back straight to the idle state. And then if we detect something straight ahead of us, we have what's called the slammy whammy, which means just go as fast as possible, and try and catch the opponent and knock them out of the ring. And so as long as we detect something straight in front of us, we go to this state. The output of the motors is set to straight, and then when we stop detecting something, we go back to search, the search state, and the motors are stopped. And notice that this is a Moore state machine. The outputs are based on only on the states and not on any of the inputs directly. All right. So that was a lot. I know, because when I first learned it, I was like, what? So any questions at all, I can give you guys some time to type it in.
So about interrupts, isn't there a type of interrupt that's controlled by timers? And what you talked about seems to be like only related to pings. So I don't know if Arduino supports like the kind of interrupt like that supports a background timer running.
Right, right. So yes, interrupts, can happen by timers. Um, Arduino, I guess Arduino doesn't have an inbuilt support for interrupts, I think, or maybe it's just not an easy accessible function for timers. However, or I guess timers as part of software. What you could do, and this is just like hypothetically, you could you could essentially make your timer like a separate device that's not on the Arduino, and attach that to a pin. And so you can say, as long as this timer is at a certain value, the timer output, the output to the pin is low, and then when that timer hits a certain value, it's high. So if you were using a timer with an Arduino, that could be one thing you're looking for. I personally haven't, or that just hasn't like popped up to me. But probably one of the other firmware trainers here can give you a better answer of how to sort of use and interrupt with just software.
Yeah. So to Lana's point, you can the timer stuff. Timer interrupts exist, and they are a bit hidden away. If you want to use them, you have to use port statements, which is like the lower level HAL. So it's not like very explicit in Arduino. You have to kind of use one step lower than that, but it's doable. But yeah, to Manos' point, it's not exactly like very common or advertised. It's like if you have to do it, you're going to have to learn a lot more about how the ports and stuff work. So it's doable, but definitely not intro thing. But good to ask about.
Yep. All right. So now it's time to get into our lab. So you can find this on the GitHub and probably on the email as well. We will be here if you have any questions. The slides are also on GitHub and on the email. So yeah, just try it out. See if you can do it. Again, if you have any questions, they're here. Thanks for attending training and listening to me for an hour.